In this video, we're going to look at atomic orbital shapes and probability density diagrams. So recall that using Schrodinger's wave equation, the shapes that you see here represent atomic orbitals, and these are regions in space of high probability of finding an electron. Each of these shapes contains 2 electrons. Now, it doesn't mean that 1 electron has to be here and 1 electron has to be here. You could have 2 electrons existing in this lobe, or you could have 2 electrons existing in this lobe, or 1 here or 1 here at any point in time. Note that all of these orbitals sit on top of each other in the atom, as you can see right here, right? And so as we increase in energy levels, we have more and more orbitals all sitting on top of each other. So radial probability distribution plots. When we graph these waveforms in 3D, we obtain 3D geometrical shapes of probability distribution. Taking the same information, graphing in 2D yields the same information only in a different form. And we're going to look at the 1s and 2s orbitals and the radial probability distribution graphs. So first we're going to start with probability density diagrams. So this right here, as we can see, the 1s orbital is a sphere. But if we take a 2-dimensional cross-section, we get this right here, where the high concentration of dots indicates high probability of finding an electron. So we're going to write that in. High probability of finding an electron. Okay, so the more concentration of dots, the higher probability you have of finding an electron. We would call this an antinode. Right? So this is where the electron constructively interferes with itself, and so you have a very high probability of finding an electron. As we move out from the center of the 1s, you can see that the dots get less and less concentrated, so over here we have a low probability. So on the outer rim, we have a lower probability of finding an electron. Now you may be wondering what the 1 and the s means. The 1 is the principal quantum number. So that means the first energy level. And the s designation is the orbital shape. So it's of the S family, which basically are orbitals that are spherical in nature. When we go to the second energy level, as we see right here, so we're in the second energy level denoted by the 2, we have an s orbital in the second energy level. And as you can see here, there are 2 areas of high electron probability. What you may also notice, though, is that there is this white region in between these 2 regions of high probability. That white region right there represents a location of 0% probability of finding an electron. 0% probability means that the electron wave has destructively interfered with itself and created a node. So 0% probability means we have the location of a node. And in this case, because it is circular in 2 dimension and in 3 dimension it would be spherical, we call it a spherical node, also called a radial node. The 2p orbitals, let's take a look at what 2p looks like. 2p, as we can see, are basically 2 areas of high electron probability separated by essentially this white space here. We see it over here as well. We've got 2 areas of high probability with this white space in between them. Okay, same thing here. The white space is obscured by the lobe right here, but it's in between those 2 lobes. So if we look over here, this is a 2p orbital, and we can see that the regions of high probability lie on the z-axis. So this right here and here, these are high probabilities. And since the areas of high probability sit along the z-axis, we write 2pz. And that's because our areas of high probability are sitting right along the z-axis. In between the z-axis is a nodal plane. A nodal plane means that all along that two-dimensional surface there, we have 0% probability of finding an electron. A nodal plane is also called an angular node. When we look at these right here and we plot their radial probability distribution plots, radial meaning radius, so that means we're looking at the probability from the radius. So we're going to start in the middle and go outward. Okay. So we can see that this graph aligns with our 1s orbital, and this is the graph for the 1s orbital. So if we look, there is a peak or a high chance of probability immediately, and then it tapers off very quickly. Well, let's see. That's for the 1s orbital. Let's go back to our 1s orbital, and let's look at this from the perspective of the radius. Well, radius starts in the middle and goes outward. And we can see, yes, right in the middle, we have high probability of finding an electron, and then it rapidly decreases. That seems to match our graph right here. High probability, and then a decrease. If we look at the 2s orbital, it's a little bit more apparent. So if we start in the middle, right here, and we go outward, we have high probability, followed by a node, and then another region of high probability. Let's look at the 2s radial probability distribution. Well, we can see right here. In fact, we have two regions of high probability. And in between these two regions of high probability, it drops down to 0, which makes sense because there is a spherical node in between those two regions of high probability. So this is your location of the node. The 2p is we're only looking at one of these lobes. Because it is a radial distribution, we're starting from the middle and we're going outwards. And as you can see, right in the middle, we have a 0% probability. So that should be reflected in the graph, and it is. Right there we have a node. And then it peaks up to high probability and tapers off. Same thing over here, node, high probability, and tapers off. So as we can see here, these graphs reflect the probability distributions you see in the density diagrams right here. Let's read this note right here. Places where the graph drops down to 0 are considered nodes. So drops to 0, that's a node. Areas where the electron wave experiences destructive interference and has a 0 probability of existing. Note, infinity is not considered a node. So even though it does drop to 0 here, it is the probability of finding an electron approaches 0, but is not exactly 0. It's only exactly 0 at a node. 0 over here in the s orbitals is the nucleus, okay? So that's not a node because for the 1s orbital, that's just the nucleus. That's why it starts at 0 there, okay? There's no electrons in the nucleus. In the 2p, it's because the nucleus is at 0, but also right in the middle of the 2p orbital, there is a node right there. So for the 2p orbital, there is a node at 0, okay? Whereas for the 1s and 2s, there's no node here. The reason why it starts at 0 is because it is at the nucleus. So that covers radial distribution diagrams and also probability density diagrams for atomic orbitals.